Hello everyone, my name is Matthias Del Campo. I'm here today to present to you the paper 3D Graph Convolutional Neural Networks in Architecture Design, which I co-wrote together with Alexandra Carlsson from Michigan Robotics and Sandra Manninger from Spain Architects. This research started with a simple question. How can we train a machine, specifically some type of neural network, to understand and replicate the inherent sensibility of an architect? Of course, this question produces an entire plethora of follow-up questions, such as the quantifiable properties of sensibility, the methodology of data harvesting, the nature of labeling, and so on. However, the primary complication in this line of inquiry is that the architecture discipline is introduced through its inherently four-dimensional nature, which rarely can be entirely captured through the very popular image-based convolutional neural networks. While there has been significant development of design techniques that hack these neural network-based 2D methods, such as neural style transfer and deep dreaming, to be used in the design process of 3D architectural solutions, these techniques are inherently limited by the loss of rich information that occurs when compressing the 3D world into a 2D representation. These developments have led to one specific question: which machine learning methods allow us to interrogate large data sets of architectural archetypes based solely on 3D models, as human architects do, instead of using two-dimensional representations? First of all, let's discuss what are graph CNNs. In this paper, we strive to lay out a new and exciting opportunity for architecture design based upon an alternative way of representing 3D objects. Instead of representing a 3D object as a pixel array in a 2D image, we propose to use a much more flexible dataset structure called a graph. In particular, we propose to use a generalization of the standard CNN called Graph Convolutional Neural Networks, graph CNNs for short, in order to model and perform the entirety of the design process using only 3D models and information. A graph is a set of nodes connected by edges. Nodes and edges typically come from some expert knowledge or intuition about the problem. For example, in design, we define 3D objects by their different geometries and shapes that manifest on multiple scales. Graphs and networks are ubiquitous in our contemporary world. Just think of social networks, biological networks, topological graphs, conceptual graphs, and of course the internet, just to name a few. What's great for architects and designers is that a standard 3D object representation, meshes, are naturally represented as graphs. They are composed of vertices and nodes, points in 3D space, connected by edges and labeled faces, based upon their location and distance to one another within the graph structure. Research involving these structured datasets has gained significantly more momentum through the development of graph-based neural networks. Examples include mesh classification, correspondence, and generation, and 3D point cloud classifications. Now we have to discuss a little bit about neurostatic labeling. This paper presents a design technique whose backbone is graph CNNs, that is capable of examining the perception and creation of architectural objects. Key to this technique is to train a graph CNN to capture the aesthetic sensibilities of a specific designer based on neurostatic labels such as a basic visual feature, for example coloration, geometric features like scale, semantic properties, aesthetic quality, functional quality, and perceptual quality. The proposed approach can be broken down into several steps. We start first by generating large databases of OBJ models of specific architectural classes. More specifically, we divided them into exterior volumes and interior elements such as houses and towers for exteriors and columns, doors, and walls for interiorities. For this paper, we focused on the database labeled houses. There are thousands of models in each category. In order to train the graph CNN, the author has to classify these models in a manual and very organic way, which is also, by the way, quite time-consuming. A range of 1 to 5 describes various aspects of a model, from its functionality to its aesthetic value. We intentionally included ugly and non-functioning models in our order to train the graph CNN in a synthetic process, the difference between functional, non-functional, and aesthetically pleasing or not. Both actions together form an organosynthetic process. The next step is training a graph convolutional neural network on this dataset to learn a function and mapping between 3D models and visual qualities as well as visual feature space. Note that this model is effectively learning architectural taste and aesthetics as defined by the architect's labelers of the dataset. However, what is unclear is if the neural network will learn to associate the same visual features with pleasing as an architect does. The paper explores these possibilities by presenting experiments that visualize the learned features of this trained graph CNN by implementing the 3D correlate of deep dream and visual saliency mapping. In conclusion, it can be stated that the final step is placing the trained graph CNN into an optimization framework that takes in other 3D models as input, and then optimizes and deforms this model for a user-specified visual aesthetic or functionality label. For example, a user could input a plain cube, specify that the aesthetic quality of a cube should be optimized, and the framework will iteratively deform the mesh to resemble the learned aesthetic captured by the dataset. We demonstrate that this optimization framework will very accurately mimic and approximate the sensibility of the architect that labeled the 3D model dataset, and will thus allow users to deform meshes in the same way that the architects would edit and modify the input mesh themselves. In conclusion, it can be stated that provided a large dataset of 3D models produced by one hand and distorted to create more variation, forms the base for the theory that a graph CNN can interrogate those models for underlying rule sets. These rule sets can generate architectural results that comply with the aesthetic criteria of the user.